Thank you everyone for attending. Just a very short introduction to who I am. As Christian said, my name is Neil Bishop. I've spent most of my working life involved in the combination of fatigue, finite element analysis and dynamics. I've been involved in or around this topic with MSC for nearly 20 years. In fact, on the front screen of this slide, it says that we're going to talk today about Nastran Embedded Fatigue, which is actually a combination of two different types of expertise. It's the expertise of MSC and their CAE expertise, with ENCODE and their fatigue expertise. ENCODE and MSC Software have been collaborating in this field for well over 20 years. In fact, they were the first, they produced the first major commercial product that it works in this area called MSC Fatigue. So I'm delighted today to be able to talk about a major new development in this technology. So I'm going to talk about solver embedded fatigue. In this particular case, I'll be talking about Nastran embedded fatigue, but the concept is general. It's a very simple concept with quite dramatic consequences, and that is to take something that has always been treated as a post-processing operation, that is fatigue analysis, always been treated as a post-processing operation done after the calculation of stresses, and combine that simultaneously with the stress calculation. So that simple conceptual change results in quite dramatic benefits, and that's what I'm going to talk about over the next 30 or 35 minutes. I'm going to try to leave plenty of time at the end for Q&A. So the general outline of the presentation is shown here on the second slide. I'm going to give a little bit of background on fatigue analysis. I'm then going to talk about how those tools, those techniques for fatigue analysis have been embedded inside the finite element environment. I'm going to talk about how that's been done in what you might call a conventional way or traditional way with products like MSC Fatigue and other similar products. And that will give me the opportunity to explain how solver embedded fatigue is different. What did we do to make this change? I'll then talk briefly about the benefits that you get from combining the two processes together. These are essentially that the process becomes faster, involves much smaller files, it's much simpler, it becomes altogether more portable, it's much more visible or transparent to the user, and it gives the opportunity, because we can now do proper optimization for fatigue, it gives the opportunity for better designs. I'll then talk about what's going to be in, or what is in the latest release of Nastran, that is Nastran Embedded Fatigue 2013, came out about 1 month ago. I'll talk about the current capabilities, and then I'll talk briefly about what's going to come in future releases. And then I'll finish off with a brief look at some of the card entries that are used for Nastran Embedded Fatigue, and I'll finish with some examples. So first of all, let's start at the most fundamental level. What is fatigue? And I always find this interesting that when we talk about fatigue, we're talking about normally talking about a very specific thing, and that is using stresses or strains as a means to estimate or predict how long something will last or how long it will take to reach a point which we will call failure in a process. What's interesting about that definition is that there is no mention of a crack taking place whatsoever. So I'm actually showing in the background a physical crack growing through a material, but our definition of fatigue as we normally use it takes no account of this. So in fact, we're treating the process of fatigue analysis as a kind of a black box. We're taking deformations from whatever source we're able to get them, stresses or strains, and we're using those to estimate or predict something about the fatigue life or the fatigue damage that's going to occur on a structure. So it's really important to realize that that's an entirely empirical process. Doesn't mean that we aren't quite good at it, because we have become very good at modeling that black box. And part of what I'm going to talk about today is how we're going to do that in a sophisticated way inside the solver. But it is quite important to recognize that this particular definition doesn't really treat the material science in a particularly good way. There is an alternate approach, which is to do a crack propagation type calculation, usually coupled with some kind of damage-tolerant design philosophy. And that approach is much more sophisticated, but that's not what I'm talking about today, and that isn't what we've embedded inside Nastran. Now, there is no fundamental reason why that can't be done in the future, and that may well be something we look at. But today I'm going to talk about conventional fatigue methods embedded inside the solver. So I mentioned there that we're considering the process of fatigue analysis as being an empirical proposition where we take stresses or strains and we use them to estimate fatigue failure. The traditional or one of the more normal ways of specifying this would be in some kind of diagram with stress or strain on the vertical axis and fatigue failure in cycles on the horizontal axis. So what we're saying here is that fatigue is controlled by the range of stress that exists in a particular time history. So you have to have a time-varying stress or a fluctuating stress, and then it's the ranges of stress which then are used to determine fatigue failure, or at least they're the primary factor which is used to determine fatigue failure. Another factor, perhaps not quite as important but still very significant, is the mean stress level that exists in the cycle. So those two things are normally what we might call primary effects. We then have a number of what you might call secondary parameters that are part of the process. So we typically need to be able to deal with block loading. We need to be able to deal with irregular sequences. We need to be able to deal with notches. And so over the last 100 or so years, a number of techniques have been developed to account for these effects. So the purpose of a commercial fatigue code is to give the user a way to control these various parameters, is to give the user a reasonably easy way to define how to do this, what I call stress conditioning. So there's a certain amount of work needed on the stresses before they can be used to do a fatigue calculation. Once you've done this conditioning, once you've got the stresses into the right form, the connection with FE is essentially a simple one. The question is, can we accurately obtain the stresses or strains from a finite element model? Can we at the same time get accurate material properties for the material we're using? Because if we can do those two things, we normally assume that we can get the fatigue life in cycles in a reasonably accurate way. So there we have it. Two major inputs, stresses and materials, allow us to predict life. And built into that concept is something we might call similitude. And that is, if we are doing this calculation within a finite element environment, then we need to be able to get the stresses from the finite element model in exactly the same form as the stresses occurred in the test coupons that were used to generate the material properties. Typically, we would use 20 or 30 coupons to generate material properties. Those the tests used to load those coupons would have been designed in a very specific way to create very specific types of stresses, typically zero mean, constant amplitude, uniaxial stresses if we can. And so we have material properties that are for very specific kinds of stress conditions. So the question then becomes, can we handle the FE model in such a way that we can make the assumption of similitude? And at first glance at this question, the answer has to be no, we can't. And that's where the commercial codes, the good commercial codes come into their own, because they allow the user to, as I say, condition the stresses that occur on the FE model in such a way that we can force similitude, that we can make this assumption valid. So that's really what we're trying to do when we do fatigue calculations inside a finite element environment. We also have another big issue to deal with, and that is the issue of potential structural dynamic response. So if you've got a structure which is going to behave differently under time-varying load than it does under static load, then you need a way to incorporate dynamic behavior. And again, the good commercial codes will enable you to do this. They'll enable you to do it both in the time domain with a transient dynamic type of dynamic calculation, or indeed in the frequency domain, although that is much more of a challenge for some of the commercial codes. So this is the background to why we tried or attempted to combine these things together 20 years ago. It's the background to why products like MSC Fatigue were created. And so really then it's a good point to look at how a traditional epi-based fatigue analysis works. MSC Fatigue follows these types of processes. And so typically, in order to run a program like MSC Fatigue, you need three inputs. You need your material properties, you need your loading, and most important of all, you need stress information from a finite element analysis. So clearly there we're showing that stress is an input and fatigue is a post-processing operation done on stresses. Now we can do all sorts of very complicated fatigue calculations in the middle box, and based on whichever method we've chosen, we can output results like contour plots of damage, contour plots of life, different sensitivity studies, all sorts of different kinds of output. The key point, though, is, let me say it again, that fatigue is a post-processing operation on stresses. So what does that mean? Well, if I now look at the processes underneath this type of analysis, we see typically that we have a stress solution process and a fatigue solution process. And so typically in any conventional approach, the designer would first run, for example, Nastran, generate his stresses, then switch Nastran off, open up the secondary fatigue process wherever it exists, and then the first thing he has to do is read in his stresses, start to define loads, define materials, and then proceed with his fatigue calculation. So quite a distinct separation of processes. And if we see how that works in terms of a data flow, again, I'll use the example of Nastran. Let's assume we run Nastran. Let's assume it was a static analysis, so the solution routine that would be used for that would be, for example, solution 101. This would produce an output file, for example, an OP2 file. Now, for some types of models that are very big, those OP2 files can also become very big. It's not unknown for those OP2 files to become very large, 100, maybe 200 gigabytes. So very, very large files to handle. So now I talked about the secondary process for fatigue. MSC Fatigue actually works within Patran. So you might even call MSC Fatigue Patran Fatigue. So you start Patran up, and first thing you have to do then is read the OP2 file, read the stresses into your new environment. Now I'm giving the example of Patran, but really the following comments apply equally to all commercial solvers. Whichever commercial solver is being used, there must be a mechanism to read in those stresses. In Patran, in MSC Fatigue, it takes place in two steps, because first of all, you connect the stresses to the Patran database. And then the second thing you do, once you start to define your fatigue job, you specify all of the various parameters that you want to use in the fatigue analysis, get to a point where you run the fatigue job. And the first thing that happens is that Patran or MSC Fatigue reads the stresses and conditions them and puts them into another file called an FES file, FES file. So there we've got three different versions of stresses. In other cases where Patran isn't involved, that might involve two different sets of stresses. Those are then treated as an input to the fatigue process. Materials are also required. Loading is also required. And out at the end come fatigue results. Now what's interesting, if we look at the overall process, the input to Nastran, even for a very big model, would have been probably around 50, 60, 70 megabytes. The results from Patran at the end, the fatigue results, would also be relatively small, maybe a similar size, 50, 60, 70, 80 megabytes. The intermediate files that we have to generate with stresses in are enormous, maybe 200 gigabytes. So we have the required output, the required input, and all of the stresses along the way are really quite superfluous to the end result. In fact, what do we typically do with them? Throw them away. So the concept of solver embedded fatigue is to recognize the fact that those stresses aren't actually needed. Take the fatigue solver and embed it directly inside the stress solver in order to be able to do fatigue calculations simultaneously with the stress calculation. So that is basically the concept of solver or Nastran embedded fatigue. Do have one process, one stress calculation, or actually it's not actually even necessary sometimes to calculate the stress result, one fatigue calculation at the same time, only to keep the fatigue result and only output that into the output file. By doing this, we can dramatically increase the speed of calculation. We've got various estimates for this at the moment, but I'll mention later on an example where we think that there is probably a fundamental increase in speed of about a factor 5 or 6. That increases if the traditional approach is somewhat inefficient, which is sometimes the case. We get much smaller file sizes, and because these stress files sometimes limit the type of analysis that can be done, we think that's going to be a big improvement in the overall process. It's a much simpler process now because you don't need to have a whole bunch of intermediate data. I'll talk about that a bit more later on. Also, because everything can be put into the Nastran input file, the whole process becomes portable. You can easily zip a Nastran input file up, email it to someone else the other side of the world, they can open it up, and instantly they have access to all the same data that you have access to. It's also very transparent because the method of running the job, the definitions, the parameters, the instructions are all absolutely clear and visible to the user. And finally, we have almost as an additional benefit, that's a really fundamental one, the ability to do optimization for fatigue. And I'll talk about that in a little bit more detail later on as well. So just going over those in a bit more detail, it's faster because you don't need to create, move, translate OP2 files, stress files. So as soon as Nastran Embedded Fatigue has access to the loading and the materials, it can immediately be calculating the fatigue results. So there is a fundamental improvement in process there. Now, I said earlier that we think that probably means an improvement in process of about a factor 5 times faster, but we have had examples recently where this has been as much as nearly 40. So we did a recent benchmark in Germany for a major automotive company, and they found they suddenly had an improvement from 44 hours to 1.2 hours. So there's some significant improvements in speed and also significant improvements in the size of the files that have to be handled. It's much simpler because if you look at the files that have to be handled in what you might call the intermediate process, i.e. the stage between stress calculation and the fatigue calculation, you can in some circumstances have hundreds, even thousands of files to handle. These are a mixture of stresses, loading, and materials. Now, these are awkward enough to handle in themselves, but they also open up the possibility to make mistakes. So having all of that stuff in the middle is not ideal, and so a simpler process with one input, one output is a much better arrangement. Also, with one input, which is an ASCII Nastran text file, it means, as I said earlier, that the process can become portable, and it's much more visible and transparent to the user. And then finally, we have the benefit of being able to do optimization. So I'll talk about that a bit more later on, but essentially, this is an additional constraint in the existing solution 200 routine of Nastran. So you can now optimize with, as well as doing it for example, yield stress, you can also include as an additional constraint fatigue life or fatigue damage. So we've been working on this for a couple of years. The first release has just been delivered. Nastran Fatigue 2013 was released in June. This is a major release. It includes a full stress life solver, a full strain life solver. Factor of safety is included for both methods, and so is critical plane analyses. There is also the capability to do parallel processing, and there are also a bunch of utilities tools that are included with that release. Nastran solution routines that are supported are Solution 101 for statics, Solution 103 and 112 for transient dynamic, and Solution 200 for optimization. Now, sometimes people ask, why do we have both Solution 103 and 112? Very simply, it's for to enable the connection to atoms to take place. If you want to combine Adams multi-body dynamic capabilities into this process, then you would typically choose solution 103 and then send the NEF file out to Adams, bring back the modal loads, and continue the calculation in Nastran. We are already working on future releases. Urgent to us are the capabilities of spot weld and seam weld, so those are already being worked on. We're also looking at vibration fatigue, short fiber composites, thermomechanical fatigue, and a number of more specific types of capabilities. Solution routines in Nastran that we're looking at are solution 400 and solution 109, as well as solution 111. So that's what we've done in terms of the solver. We've also been working very hard on the pre and post side of things. So obviously the pre and post that we have control over is Patran. So Patran 2013 has been enhanced to support Nastran 2013. And so you can do both pre and post support of Nastran Embedded Fatigue in Patran. So if you want to set up a job and write the appropriate instruction file with Patran, that can be done with Patran 2013. I made a note here that for non-Patran users that want to do this pre-processing, there's a very straightforward way, and until the point when their preprocessor of choice has this capability, which I would imagine won't be too long, in that intervening time, the best way to do that is by a simple editing of a template system, which we can help you with, which is a rather straightforward thing to do, and I can mention a bit more about that later on. This presentation doesn't include any overview or demonstration of Patran for that pre and post processing work, but that will be covered in another webinar shortly. In terms of post support, as I said, Patran will do that. You can either do that through use of something called an FEF file that is produced, or through the OP2 file. The OP2 file does now fully support fatigue results in that file. So that's one option, is to go the route of using Patran. Alternatively, you can use one of the other types of output files that are created. For example, there is an FEF file that can be read into Metapost, Beta Systems Metapost. I understand that Beta Systems are already in the process of updating their systems to read the fatigue results in the OP2 file. That may already be done, so it may be that Metapost can read the fatigue results out of the OP2 file. So there are a number of options. There's also an HYP file that's being written once we release 2013 shortly, 2013.1, and that will be suitable for reading into the HyperWorks system. So let me just make a few comments about the instruction cards, the instructions, the control file that we essentially use to run these jobs. It's all done through the Nastran input file, the Nastran bulk data file. For those of you that are familiar with that, you'll know that that is essentially an ASCII input file. This is, in terms of fatigue, is about 10, or maximum of about 10 card lines that have to be written. The first one that is required is what you might call a fatigue output request. In case control, there has to be a card that says fatigue, and that simply tells Nastran to anticipate that it's going to be asked to do fatigue calculations in its process. This is a very interesting card because there's a lot of detail here which sometimes isn't necessary, but the simplest form of this would be fatigue equals a number, let's say 10. That ID, that number, then references all the bulk data entries that are then going to be needed for that fatigue job. The point I want to make, though, is it doesn't only have to be one ID. You can have 2 or 3 or 5 or 10 or 100 IDs there. In fact, you can put those IDs into a set and reference the set. Now, why would that be relevant? Because this, I think, gives you for the first time the ability to do, for example, Monte Carlo simulation with fatigue as the output parameter. So this gives all sorts of interesting opportunities that haven't been yet looked at for varying various parameters in the input to see the effect on response. So that card tells Nastran that there's going to be a fatigue analysis requested. The next thing we have to do is specify a number of bulk data card entries. And as I said earlier, this can be as little as 1 card or 2 card entries. Most of the data that has to be defined is optional. In other words, if you don't put it, default values will be used. Essentially, the card entries fall into 5 categories. There's one section which tells Nastran which parts of the model to do the fatigue calculation on that. So we have something called a fatigue depth card, which specifies that, along with a brand new set card in Nastran called set 4, which is a way to group parts of a Nastran model based on its element properties. So those 2 things define where to do the fatigue calculation. Then we have 4 cards which together define loading. Very complicated, sophisticated loads can be specified through a combination of these load cards. We then have 2 cards which define types of material properties. We have a matte FTG card and a property card called PFTG. And then we have something called fatigue palm, which defines many of the detailed parameters needed to do the fatigue calculations. So without going into too much detail, I'm going to just pick out a few of the details from these cards to give you an idea of how sophisticated a process can be set up inside the Nastran environment. So let's start off first of all with the fatigue depth card. This is a way of telling Nastran which parts of the model to do fatigue calculations on. Now we have a number of options for this. One option is to just put fatigue depth and an ID and let the calculation take place on the whole model. But then you might need a way to speed things up, because that might get rather cumbersome. So we provide something called top stress, which is a way of pre-filtering the model based on damage. And you can use that, for example, to filter out 95, 98, 99% of your elements and only report back on the 1 or 2 or 5% most damaged elements. Or you might want to have a much more refined way of specifying groups using things called L-sets. So this allows you to define parts of the model based on Nastran sets. So that's the fatigue depth card. The next card that I'll just talk about briefly is the materials card, matte FTG. This will show you the level of sophistication that's embedded into this product, because here we have 1, 2, 3, 4, about 8 lines, each of which is optional. So you can, these are intended to be used in such a way that they allow you to put in your material properties in the form that you want to put them in. So for example, the 3rd line here, SN, allows you to specify your material properties in what you might call the encode material format. The table option allows you to specify them in XY points. And so you have all sorts of options here, and if I graphically show you what that means, if it's the encode format, it's a specific analytical formula that's used to generate the SN curve. If it's XY points, then this gives you complete flexibility on the shape of the curve. But sometimes you might want to have different curves at different mean stress levels. So that's also possible with that table function. You can specify different SN curves at different means or different temperatures, or whatever it is you want to do with that. Now what you'll notice, if we've got a set of data there which is stress range versus life and different curves for mean, essentially we've got a 3-dimensional SN diagram. So you can choose to move that round and slice it the other way. And what you have then are what we might call Hague diagrams of constant life. And those are also possible as an input type to this process. So really quite sophisticated. Maybe your material properties are in the form of strain life data, and that is another alternate way of putting your material properties into this process. So really, it should be possible to enter the data as you use it into this system. Another card that's interesting is the fatigue palm card. This is where a lot of the detailed instructions about how to do fatigue are included. For example, what stress combination to use, what means, that is like von Mises or principle, what mean stress correction to do, how to do the rain flow cycle counting, whether to do factor of safety analysis. All of these types of questions are answered in this card entry. Another important card entry is the ability to define loads. And these are done, as I said earlier, through 4 different cards. The first one is a fatigue sequence card. And this, in simple terms, specifies how long to apply a certain load before moving to the 2nd load, the 3rd load, and so on. So in practical terms, this means, for example, you might want to apply a certain condition like a steering lock to lock for a certain number of seconds. cobblestone slalom, which is event 3 for a specific number of seconds, and you want to do these different events one after the other and then add up the damage. So that's possible with the sequence card. Now, each of those events may be made up of more than one load time history. So we have to have something called a fatigue event card, which allows us to bring together the individual loads that themselves then create a single event. So here I'm showing a fatigue event card with 8 or more loads, but if I show you graphically a typical example, here we have an event with 3 load time histories applied, X, Y, Z. So in that particular case, we would need an event card with 3 loads applied. Then you need, for each of those loads, if I go back to that, for each of those loads, you have to assign or tag with that load time history the stress subcase that is going to be generated with Nastran. So for that, we have something called an FTG load card, and on this card entry, you will see a reference to the time history as well as the Nastran subcase. So this card, FTG load, connects together the load time history with the stress field that is needed for the fatigue calculation. So again, rather sophisticated tools provided in order to be able to put these things together. The last card I'm going to mention isn't a new card, it's an updated card. It's the DRESP1 card, and this is the card that is normally used for optimization for design sensitivity. And what's happened here is this card has been updated to include fatigue as a constraint. So now this is an additional option that is available to you when doing optimization type calculations. So that's a very brief overview of the cards. If you wanted to see those in more detail, the new Nastran Quick Reference Guide 2013 has details of all of these things included. So if you want to find out more, then that's one option. Another option is there's a very nice fatigue user guide that has been created to go with this product. And that also has, as well as a detailed explanation of these card entries, it also has a set of very nice examples which go through using these card entries to do particular kinds of fatigue calculations. And that's what I'm going to show briefly to finish off the presentation today. So I'm going to show first of all some of the case studies that exist in the user manual, and then I'm going to show a couple of other case studies that we've been involved in more recently. So in the user manual, you'll find a series of examples, starting off with something rather simple, a keyhole specimen, with either a simple fully reversed load or a time history applied. That's a solution 101, so it's a static analysis with a stress life approach. There is also a spider model with a simple loading. That one is analyzed with strain life. Then there is a keyhole, a mountain lug specimen, which is analyzed with stress and static analysis, but with very complicated load histories. There is a shock tower with complex multiple loading, and that introduces the idea of duty cycles as well. That's a static analysis done with strain life. And then finally, there is a beam model which is analyzed with all the available solution routines. So solution 101 static, solution 103 atoms with atoms, and solution 112 with transient dynamic. So that goes through the 3 methods and shows the card entries for each. So those are available. If you're interested in this capability, then I would recommend you look at that user manual and look at the quick reference guide. I have a couple of very short examples on optimization, and I'm going to show these to bring out 2 different ways of considering the use of optimization in fatigue. The first is something which is a very interesting concept, that generally in fatigue analysis, we normally only check for fatigue as a parameter rather late on in most design processes. So we typically design for other things, and then right at the end we check to see whether fatigue is okay. Now what that means here is we start off with a beam as shown on the left-hand side of this slide, and we proceed with our design, and we only use stress as the controlling parameter. In this case, we're asked to find out if the beam is fixed in a wall on the left-hand side and it's holding up a load on the right-hand side, how much can the beam be minimized along its length whilst still being able to maintain that load in an integral way. If we do that based only on stress, we get a 39% reduction in mass. That's great, except that in doing that, we violated our fatigue failure mechanisms. So what we could have done is we could have started at the beginning and optimized on both at the same time. So optimized based both on stress and fatigue. In this case, we still get a mass reduction of about 13%, but we keep fatigue life within acceptable limits. So that's really what we would now encourage. We would say, if you're doing stress analysis, then right at the beginning, why not do fatigue analysis at the same time? That would really be our recommendation going forward. The second optimization example is slightly different. It's more of a conventional optimization procedure, where the example that we're looking at is a shock tower in a car which has multiple elements to the overall part. In fact, it has 15 different panels, each with its own thickness, and the objective is to see whether or not the thicknesses of those panels could be reduced. So we want to minimize panel thickness and overall weight. But at the same time, we want to improve our fatigue life a little bit. So we want to improve the log of fatigue life from 0.7 to 0.8. So how do we do that? Well, we set up this job in Nastran in the conventional way, using a conventional solution 200, but we include the additional constraint of fatigue in the analysis. And we then proceed to minimize the error of the solution over a series of iterations or design cycles. So in this case, we have 15 iterations of this solution. And we can see here that around the 8th or 9th cycle, we have a pretty good solution. So we've minimized the error of the solution by around the 9th iteration. If we look at how that shows up in terms of the thicknesses of the panels, of the elements, we can track each individual panel separately. So here we have 15 different panels. We're looking at the thickness of each, and what's interesting is that some of the panels actually increase in thickness. I think there are 3 of the panels that increase in thickness. The other 12 reduce over a design iteration. So if we combine those together in one single result, we see the effect on mass of that solution, of those design iterations. And after about the 8th iteration, we find we have got some improvement, some reduction in weight. And if we summarize that, we see that we're able to reduce weight by around 24%, whilst at the same time increasing life by about 14%. So we think that's a very nice outcome, and we're really looking forward to seeing this being implemented in some more commercial products and commercial designs. So I'm going to finish off with one last example, which is an interesting example because it's something that we analyzed many years ago, more than 10 years ago, with what I called earlier the conventional methods. MSC Fatigue was used to analyze this particular vehicle. And when we did this, I think it was 12 years ago, it was rather a challenge because we were reaching the limits of our capabilities at that time with MSC Fatigue. So we wanted to see 2 things. So this is the truck that we were looking at. We wanted to see 2 things. We wanted to see how much processes have improved over those 12 years. In other words, we ran this before with MSC Fatigue. How much better would it be today with MSC Fatigue? And just as a benchmark there, let me mention that this took around 160 hours to analyze 12 years ago with MSC Fatigue. So the first question was, how much quicker would it be with MSC Fatigue today? And then secondly, what benefits would we get of using a solver embedded fatigue approach? So those are the 2 things we're going to look at. So that's essentially the requirement of this analysis. So just a little bit of background. This particular example has, I think, 4 mount locations with 3 loads per mount. So 12 inputs, 12 simultaneous inputs. Those would together create events. And then there were 11 events. And so in total, 132 time histories were required. And altogether, they created 3 6.8 million data points that had to be applied to this model in terms of loading. So those are the 11 events that are applied, different kinds of load conditions. The model itself was a relatively small model in today's terms, around 100,000 elements, with around 600,000 degrees of freedom. So not particularly challenging today, more challenging 12 years ago. The material requirements were that we had to analyze this both with stress as a material property and strain. So stress light and strain light were both used in this analysis. It was very much a dynamic problem, so we had to also look at the various modes included in the system. Here we have 15 modes, 6 of which are rigid body modes. So these had to be taken account of in the overall process. So this was actually done and presented at the 50th user conference, MSC 50th user conference in Santa Ana in June. So if anyone wants to get the full details of this, those are available. So I'm really just going to skip to the results and try and talk about the process improvements that we got. So in terms of results, these are graphics of the fatigue life over the model, or fatigue damage rather, over the model. These are shown with MSC Patran. As I said before, MSC Patran will be the subject of another webinar to show how it can be used with fatigue later on. So those are the sorts of results you get. You can go down into the local areas and look at those results locally. And here we have, not only do we have the fine element-based results, but we also have some indication of what happens experimentally when this was tested, which is very nice. So we have lots of these results. And what's interesting is how nowadays there isn't very much argument about the validity of these fine element-based approaches for doing fatigue and durability calculations. Here we can see that they are very good at calculating locations of damage. I think it's fair to say they're less good at calculating the absolute number of a failure. In other words, if the real part fails after 100,000 hours, then you shouldn't have a requirement to be within 10% of that for sure. Maybe you should have a requirement to be within a factor 2 of that result or something similar. So maybe don't be too ambitious about the absolute number, but they should be able to give you the locations of critical damage. And what they can also do is tell you what happens when the design changes. So if you've got an existing design and you want to know what happens when you change it, that's another area where these approaches really become very powerful. So I'm going to finish off by talking about the numbers of how long it took to run. So I said that when we ran this 12 years ago, it took 160 hours. So if I'm presenting this in a live audience, I usually ask for people to guess what the number is today. I think you'll be surprised to know that MSC Fatigue ran this in 2 hours. So from 160 hours to 2 hours, quite a dramatic improvement, primarily because of the hardware. And the next thing then is what happens when Nastran Embedded Fatigue is used. Well, there is a further reduction in time down to 24.5 minutes. So 118 minutes for MSC Fatigue with new hardware, new software, 24.5 minutes for Nastran Embedded Fatigue. There is a difference of about a factor 4 or 5 in between those two approaches. We think that is probably a fairly fundamental difference between GUI-based conventional approach and a solver-based approach like Nastran Embedded Fatigue. But that only tells part of the story, because the next question is, how much time does the user spend managing the intermediate process? There are two parts to that question. How much time does he spend handling files? So here we have an indication of the file sizes required for MSC Fatigue. We need about 282 gigabytes of file space for MSC Fatigue. Nastran Embedded Fatigue took 31 megabytes of space. So dramatic reduction in the size of the files that were needed. Coupled with that are the number of files that are needed. Because this is a transient dynamic, there was a requirement to generate modal loads. You need a modal load for every input time history and every mode. So there are 132 modal loads that have to be generated. There are then various other files. Altogether with MSC Fatigue, this makes around 191 files. With Nastran Embedded Fatigue, there are just the 2. So just to summarize, then, there are 3 different areas of benefit: solution time, ease of use in terms of number of files, and ease of use in terms of size of files. So, we think those are rather important benefits of this new process. So that brings me to the end of the presentation. We think this is a major enhancement to the way fatigue life can be done. We think it's the most important development in CAE fatigue since the introduction of MSC Fatigue. I mentioned earlier that there are lots of documents available. There's a quick reference guide and a user guide and a release guide. So if anyone would like to take a look at this, then please get hold of your local MSC software representative. So thanks very much.